This is the 51st Flow Talk, where Flow stands for Federated Learning One Word Seminar, of which aim is to provide a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. Today, it's my great pleasure to introduce you our speaker, Andreas Hellander, who is an associate professor in scientific computing at Uppsala University in Sweden, and he is also a co-founder and CSO of Scalable Systems. And today, he's going to tell us about his recent work on scalable federated machine learning with FedN. So thank you, Andreas, and the stage is yours.
Yes, thank you so much, Samuel, and thanks for organizing, inviting me. It's great to be here. So like Samuel said, my name is Andreas, and I come to you with two hats today. So I have a research group at Uppsala University, at the IT department, with its roots in scientific computing. And then we also, so this project is done a collaboration with our spin-out company, Scalable Systems. So we developed FedN together then between the lab and the company as an open source project. Yeah, and I will tell you today about, this is essentially a software talk where I will not talk much about background of federated learning. I assume in this audience, all of you are familiar with this. Also not so much about the theory, but rather about our implementation decisions and design aspects of what we think is a very resilient and scalable implementation of hierarchical federated learning. So this is what FedN is about. And a key contribution sort of in the paper we wrote in this talk will be then some real world results from systematic benchmarking in live distributed environments. But first, I thought I could just a little bit give you a little bit more of a background of where we are and what we're coming from. So together with some other PIs, I run what we call the Interactive Scalable Computing Laboratory at Uppsala University, where we have many different focuses. Distributed computing is at the core of all of these. And in particular, we do a lot of our work in applications of distributed computing to compute and data intensive problems in science. So much of it comes from life science and systems biology, but also more recently, we do a lot of work in distributed AI. That sense. So we're a group about 10 people on and off, having quite fun developing different things. And then Scalable Systems, the spin-out, was founded in 2018 with a focus on open source. We are a couple of different co-founders with different backgrounds. So we have entrepreneurs with experiences of building companies in med tech and also in sort of security intensive companies such as Saab and Autodesk. We are an R&D intensive company. As you can see, we have 4 associate professors in the founding team, and we sort of regularly publish papers and so forth. But the main thrust of the company is to address this challenge that we're seeing when infrastructure in the cloud becomes more and more distributed. So privacy is definitely part of this, privacy preserving machine learning. But I would say our sort of even strongest interest would be in this challenge that comes from a highly distributed cloud, decentralized cloud. We work with a couple of companies, mostly in Europe so far. You can see here it's been sort of expanding with collaborations over time. So, but I will tell you a little bit more of those towards the end of the talk if it's time. Some case studies of work we're doing with FedN in applications. But this talk is about the framework. So FedN is, as I said, an open source framework for federated machine learning. In particular, it's an implementation of hierarchical federated learning. Our key sort of design aim, or one of the aims we have here, is to have something that is as production grade as possible given the state that federated learning is in today. So we have focused a lot on the distributed computing aspects and scalability. So some of the key challenges that we see there when it comes to scalability, as we are well aware, is that in a simplistic setting or implementation of federated learning, you will have one server that coordinates model updates and aggregations for a number of clients n, and the challenge being there that n can be potentially a very large number, ranging from hundreds to millions. This is, of course, fundamentally a traditional client-server problem, and there will be many different types of implementations that we can consider here. More or less standard situation. But I mean, the challenges comes from many things like weak connections that will lead to communication bottlenecks. In particular, large models, if you have very large neural networks that you want to train locally on the clients, you definitely run into network bottlenecks quite quickly for a small number of clients. So essentially, I mean, the challenge, as we know, is the server will become a bottleneck in this situation. And then there are, in principle, two possible solutions to this problem, right? The first possible solution would be that you still stay with this kind of simplistic implementation with one aggregation server, and then instead subsample clients in each round so that you try to keep them at a manageable number. But as we have seen, it's often better. I mean, it would be desirable, of course, to be able to use as large as possible set of clients during updates. So the second solution, which is quite obvious, is to add more servers or aggregators or combiners, and then do hierarchical updates. Yes, Sam? Was there a question?
No.
No, I thought you raised
no
your
question.
hand. Yeah, it's quite clear. Yeah, so then you sort of keep the algorithm reasonably simple, some complexity in respect to the hierarchical updates, but in principle, you add more servers. So this is the approach that we have taken in our implementation, in our software. So it's a hierarchical federated learning model. And we can illustrate it like this. So we have this pretty much three tiers. And these names here, I will come back to them in the talk. That's how we have chosen to name different components in the framework. But on the bottom layer, we have a set of geographically distributed clients. Then we have combiners, which can be one or many or more. And these are often what we call servers in the literature. We call them combiners or aggregators. So these are servers that are then responsible for aggregating a subset according to subset of clients. And then on the top level, we have what we call the reducer, which can be a component or a service that then aggregates partial global model updates from combiners. So this is quite a simple picture. You can also write this in math, of course. So I will put the reference towards the end that I think gives a quite good exposition of this. But in principle, it doesn't become any more complicated than sort of traditional. So if you do this with federated averaging, for example, you can just formulate this down as a nested algorithm. And you can show that this converges in quite reasonable assumptions. Obviously, you recover the standard implementation or setting for the case of one combiner then. And then in this case, the reducer layer just becomes a sort of identity operation, almost like a simple serving or forwarding module in that situation. This is all, I would say, so to summarize, I mean, this is the approach we have taken in FedN. And I will come back a little bit.
Sorry, Andreas.
Go ahead.
We have one question. So there is a question by Konstantin. I'll try to unmute him.
Thank you. I think so. I mentioned in the chat. So in the previous slide, the computation pipeline looks very similar to Hadoop MapReduce systems. So they, in this MapReduce paradigm, they also have mappers, pre-combiners, and final reducers. But
Exactly.
Hadoop do not cover partial participation. So
Sorry, I couldn't hear the last.
did you think during your work to reuse Hadoop, or you decided not to use it?
This is a very good question, and actually, also we talk about this in the paper. That yeah, this is pretty much inspired by the MapReduce paradigm. So actually, and this is a little bit history. Before we started reading a lot of the federated learning literature, we actually came to this problem from the background of working a lot with MapReduce, and decided that this was a fun problem for us to work on. And this was many years ago now, and decided to go with this kind of MapReduce-based computing model. Hadoop in itself would not be a good choice to implement this due to like high latency and so forth. We did contemplate for a while there if we could implement this in Spark, if you know Apache Spark, but decided against that. So I will show you we have our own implementation, and a lot of it is of course that you need a lot of control. So it's in the end better to write a dedicated federated learning framework, not least for operational control during deployment stage regarding to security and so forth. But the nice thing, and with this observation as well, is that since this especially at least if you do federated averaging hierarchically, can be expressed as a MapReduce program, almost it guarantees that this architecture will be highly horizontally scalable and resilient. So this is all you get pretty much from computing theory.
Thank you very much. As one more question, do you support only hierarchical federated learning schema or another schemas as well, which are, I don't know, like some arbitrary connection of clients, more complicated schemas, or you mostly focused on hierarchical schema?
First of all, I mean, we of course support this case where you have only one combiner, and then you're back to federated averaging case. But yeah, the API is very flexible in that sense. I will come back to that. There are pluggable modules for how you assign and connect clients.
Okay, thank you very much.
Pretty much for a computation to make sense in FedN, it should follow this pattern. Then the implementation really comes. I mean, you get the most from the implementation. Yes. So this is another way to look at this picture instead of this kind of layered picture. And I think this has also been discussed in the literature, that what you get from a structure like this in the code is that you enable highly decentralized, model training. So you get a lot of flexibility at the deployment level. So this picture, I think, is a better illustration of what it looks like in the real setting. And why this is interesting is then because these combiners or aggregators, you can think of them in the edge computing case as mapping. I see we have some typos here. Mapping roughly to, they would be suitable to deploy on edge clouds or edge servers, fog nodes, if you come from that community. So that you can deploy them close to a certain group of clients that could, and this could be based on geographic locality, for example. So you can deploy these decentralized learning networks where then the reducer component in the simple setting where you implement that as one service could, for example, be in the central cloud or as a sort of cloud server. So in this way, you can structure your deployment on the deployment level, on the operational level, according to very many different use cases. So this gives a lot of flexibility in that sense. And here we come back to that sort of to then allowing different policies for clients connecting to reducers. So I think that this picture is sort of what you should have in mind when you think about FedN. This is the situation it enables. Coming back to, yeah, and I understand, I mean, it becomes, depending on if you have a computer science or math background, Some of these words becomes a lot of acronyms, but bear with me, I will show some results soon. So what we have done then is we have opted for, so we wanted to have both very high. We had a couple of things in mind when we chose how to implement this. And one of them was that we really wanted language agnostic clients. So we wanted to be able to implement clients in this situation for both embedded systems and for the standard sort of computer for clusters and so on. So we wanted to have a language agnostic API there. So what we have today is we have everything implemented in Python, but for that reason, we chose to work with to develop the communication protocol in protocol buffers, Google protocol buffers. So this is a way to standardize essentially message types in a way where you then can implement remote procedure call RPC with the library Google RPC in different languages. So this is what we have done. So we have clients in the framework. They are Google RPC clients. And then these combiners, they are implemented as gRPC servers. So all the communication between clients and combiners, the aggregators, is done with the gRPC protocol. And I will come back to exactly sort of how that is implemented. So this gives us two things. First of all, it gives us the HTTP2 connections. So we have, first of all, a production grade framework that is open source and also and highly resilient to connection failures. So it's very good at keeping long-lived connections with a high-level interface. So this has been very helpful. And the other is this agnostic, language agnostic setting. So we have the server, which is the bulk of the code implemented in Python, and that we think is fine for most parts of the combiner, but then the client could be implemented in so a quite lightweight client to implement in many languages. Then this reducer component, that has different jobs to do. So that's essentially a traditional Python web service communicating with clients initially. So clients ask this reducer when they connect to a federation, okay, where should I go? Which combiner should I attach to? So this is done via standard REST web HTTPS communication, where then the reducer has to talk to the combiner again via gRPC. This is a lot of work to implement it initially, but it gives a lot of at least for us, I will show you, has been quite good. So again, this reducer component that we have on the top level, you should think of that as two things, two main roles. One is in this map reduce context, where it is responsible for reducing partial models from combiners. And the other role it has, and this is partly to implementation decisions so far, is that it runs service discovery. So it maintains knowledge about all the combiners that you have deployed in the network, and it manages, as I said, client assignments. So a client will ask the reducer when it connects, as I said, for an assignment to a certain combiner, and then you have this a pluggable policy that you can implement as a user. Okay, well, how should this be done? Should it be with some round robin allocation, or should it be a first available, or should it be based on geographic proximity? So this gives a lot of flexibility as a user to implement, to swap out that behavior. And the other thing is that this is also the level where you implement the sort of controller interface around control. So this is where you coordinate training over all these combiner networks. Because this is important to understand in this implementation is that the reducer only talks to combiners, and combiners are independent. So you give the combiner a job, go and coordinate a model update, and then the combiner will do that independently for an extended duration of time. than talking to the clients. The other thing I think is done, and this is not sort of very impressive research-wise, but it's been extremely useful for us and for users, is that we actually spend some time writing a UI where you can look at model validation of clients, and you can look at, you can see and verify visually what the network looks like and how it is, what its health status is. So this also runs in the reducer. And as I said, the combiner is the main agent here, where most of the code is written. And this is the gRPC server, as I said. It's a stateless agent that is responsible for managing then K clients out of this N capital large number. And as I said, this combiner can work independently of other combiners and the reducer for long durations of time. Then again, you can look at sort of analysis of hierarchical learning for federated learning. And then of course there is like a tuning there. Okay, how long should you update? How much should you update on the combiner level, and how often should you synchronize the reducer level? So this is something you need to tune then use case for use case. The combiner also runs this aggregation part. So this is where we currently have an implementation that we have in the release version of federated averaging on the combiner level. But here you have also a pluggable class that you can replace. So you have an aggregation callback that essentially you implement as a user, and then there are, of course, black box ones in the framework that tells you what to do when you receive a model update from a client. So this is something you can then use to implement your own algorithms and experiment with different types of schemes in the combiner level. And the same on the reducer level, of course. So pretty much, there was this question before about what type of sort of communication patterns to allow, and maybe this becomes a bit answer to that question as well. So in principle, you could implement any algorithm in the framework that you could obtain by varying the aggregation scheme on the combiner level and the aggregation scheme on the reducer level. So those within that design space, you could achieve different things. But you can already there see that by doing this, for example, we can do a hierarchical federated averaging, and that is what we support currently. But we're also working on different type of ensemble methods that we can easily implement as well by sort of having individual combiners, aggregators on the combiners, and then ensembling on the reducer level, for example. So this gives you a lot of flexibility. And I mentioned the controller, which sits on the reducer. This is the main implementation of the round coordination. Again, this is a temporary class that we can swap out. So that helps you control things. The clients then are, of course, very important. And as I mentioned, we wanted to have a model agnostic framework. And the way we do this is by opting for a black box model on the clients. And this, of course, has advantages and disadvantages. But what we have chosen to do is we assume that there exists a program on the client which can read a file with a model update and do update the model and then emit the file with updated weights or model updates. And then in the framework, by implementing helper classes that tells you how to serialize and marshal models from different frameworks, you can essentially support any framework that you want. Doesn't even have to be a machine learning framework. And again, the question of MapReduce, in principle, we could implement any MapReduce program, but at some point, we of course make some assumptions to optimize things. So this is the assumption we make on the client level there. Naturally, this precludes us from doing fancy things like that we could maybe do in, say, PySwift, where you have more direct control of the data structure on the clients, if I understand things correctly. think that's what you get there. So yeah, what is it? And we can also then.
Sorry, Andreas.
Yes, go ahead.
There is a question from Constantine.
Yep.
Thank you. I would like to ask what are requirements for the network connection? Should computers be equipped like with gigabit Ethernet? Or because some people carry experiments with InfiniBand, high fast buses. So what buses did you use when you used gRPC in experiments, or I found very interesting that these combiner steps, they have separate like physical buses. So there is no like one central switch, but there are like a way to use, to alleviate communication problem, at least with this pre-combiner step. So I just want to obtain your comments regarding to used communication interfaces. Is it just usual Ethernet, or did you communicate with TCP/IP, or did you create your protocols?
I think I understand your question, but you were breaking up a little bit as well. I will try to answer. And first of all, I should say that some of these things, now I become a little bit insecure myself. So I will check with Morgan, my collaborator, who actually did most of the ERPC part on the combiner level. But I think in all the experiments we have done, we have communicated over public internet on HTTP2 protocol.
I see.
Yeah, but we can talk more about that, and I can also see if I can obtain a better answer to your question.
Okay, thank you.
I'm not sure exactly what buses the
yeah, if you have said that you use the usual fast Ethernet, I typed it's like, let's say the maximum speed, it's 12 megabytes per second. These neural networks models, even like ResNet 18, serialized models take 44 megabytes. So if you will uniquely use this like communication bus, usual internet, even there are no another packets, it will take you 4 seconds just to send the model. And if there are another like this area, this medium is shared, it will take more. So like communication is a problem. And just, okay, thank you.
That's interesting. We can talk more about that. Yeah. So the way this works in practice is that if you come and use the framework as a data scientist, of course you need to prepare then something. And we have come up with the original name for this as the compute package. And this is essentially what you need to do. You have your model probably that you have developed, and it's the blue box here, and that's a core, whatever you have done and your preferences for how you structure and develop your project. This doesn't really have anything to do with FedN. We think in cases it might be a small Python library or a library that you do. Doesn't have to be Python. But what you need to do in this package is you need to provide entry points for the framework. And pretty much you define them in a YAML file. In all the examples we have, they are Python programs, but they could be any binary program that you can execute in a command line in a Linux environment. And then you use the FedN APIs there to, and I said, these helpers to provide marshalling of files, depending or serialization and exportation of weights, depending on if you use Torch, Keras, or scikit-learn, or whatever. So you need to provide this training and validation endpoint. So there should be one endpoint that is responsible for doing a model update, and there can also be an optional endpoint for running a validation on the model. And these are typically these are the programs that directly read your local data that interface with the local data. Then there is this gRPC client I told you about, the FedN client, which has a dispatcher. So this is the one that receives requests from the combiner to do updates or validations. And then it dispatches this request eventually to the compute package. So the compute package you prepare and you upload that to the reducer when you seed the federation. And then when a client connects, it will receive this. And this is in practice a tarball. It will receive this, it will download it and stage it locally to make it ready for trade. So this is, I guess, where sort of as a user, you have to do some digging and learn how the code is structured. This is where you interface with the library. So what about validation in the framework? We have made it so that we want to be quite flexible. So as I said, we have the validation endpoint on the client as well. So you can choose to have a test set, validation set on each client or on some of the clients. The client can start and be a trainer, it can be a validator, it's usually both. And then you can also do this on combiner level, or you could do it on the central level. In that case, we don't really have any special support for it in the framework. You will do it with your normal MLOps tooling or your toolshed. But in all of our examples, we provide examples of where you do it on the client level. And this is also comes from Scalable talking to customers that in many situations, the clients in the federation would like to validate the model on their own private data. The validation metrics are then returned to the framework and visualized in different places. So I already touched upon this when we talked about the framework, but what we have made an effort, because we want this to be, well, production and scalable, but also useful for doing research and extendability. So all of these things, like I said, how should clients connect to combiners? How should they be assigned? It's something you can and the code is written largely on something called a factory pattern. So you can replace then objects or classes dynamically at runtime, like the connector algorithm or the control strategy, where you can implement different streams for how would you handle dropouts or all of these things that you would want to do. As I said, the combiner algorithm is also something you can swap out on the combiner level. Currently, it would not be easy to do different ones on different combiners, but I'm sure if you're me, it could be done. But that is something which we want to improve the API for as well. And so forth. So this is a little bit about how we have implemented and what we have chosen to do. It's hard to talk about code usually, but you can also go and read the code if you're interested. But what I wanted to do the rest of the talk is to tell you about this benchmarking that we did in the paper we have on archive. So the first thing we looked at was combiner performance for a cross-device situation. So we wanted to see in practice how will the combiner agent, the server there, handle variations in client load during different resource requirements. So what we used here, we had a postdoc in our lab, Sadi, developed a use case based on a human daily activity recognition use case data set. So the CASA data set, this was an LSTM model, and we made it quite small. It classifies 10 different user behaviors. So these are essentially readings of sensors in apartments. I think they're from Spain, from some EU project. And the model update that is being sent in the network, in this case, is 254 KB in serialized format. So this is the size of the sort of packet. I think we used the Adam optimize, so that's not particularly important. And we did, of course, these things where we checked that we actually the same or comparable results as the centralized training. So what we did here, we deployed combiners, and then varying number of clients is something. We have a scientific cloud in Sweden called the Smith Science Cloud. So this is a quite performant OpenStack deployment we have in Uppsala. So it's essentially a cloud deployed on the previous generation HPC servers. It doesn't have InfiniBand connect. It has normal Ethernet in 10 GB lines. And we use this then as a way sort of to emulate the situation where this could be an edge. The combiner is running in an edge cloud. And then we have clients that are varying in their performance, but they have at least reasonable connectivity with the combiner. So the first experiment we did was to look at a single large combiner. So we deployed the combiner as a server on an 8 virtual CPU, 16 GB RAM VM. And then we varied the combiner number from, sorry, computer kind of, yes, from 200 clients up to 1,000 clients connecting to the single combiner server. So this would be if, say, that you have a typical federated average implementation. And as you can see here, you know, when we double, we have a 5-fold increase in combiners. We had about a little bit more than 2-fold increase in round time. So what you have access is the time to do one round update. And then each client has one epochs, one local update. But this was quite, you know, expected and reasonable. I think it was a little bit, we honestly did not expect it to handle 1,000 clients, but it did. So I think this where the gRPC implementation positively surprised us. So the next thing we asked then is, okay, but how resource constrained of combiners can we actually use? So then we did an experiment where we took 600 clients deployed, and we vary the hardware specs of the combiner, and we would do this with VMs as well. So we go essentially from a large combiner like we had down to smaller and smaller combiners. And I think the smallest one was 1 CPU and 1 GB of RAM. So this would be a quite resource-constrained aggregator in the edge. And what you can see from this plot is a little bit messy, but what you want to see is the blue curve in the left plot. That is the percentage of work in the round that is done by the combiner. So essentially, when the blue curve goes up, it means that the combiner is becoming more and more a bottleneck. So the furthest to the left there, you have the situation with one large combiner. We had about 29% of the total work in the system being done at the combiner level. And then what is interesting there is that you can see the strength of this hierarchical model, because then we can also go and replace that with 3 small combiners with 1 CPU less. So it has in total a little bit less hardware resources. And you can see that the sort of the total combiner load drops to 9% on each combiner. So we have sort of comparably more work done per CPU unit on the client. What we also gain here, of course, is additional resiliency. Because if one combiner dies, nothing horrible will happen to the system. Whereas if you only have one, you're really in a non-robust situation. I thought it could be fun as well to show on the right plot there, the histogram that you see, that's the distribution of client update times. And this we got quite naturally because for practical reasons, we didn't have access to insane amounts of hardware. So I think we deployed clients on, maybe it was 10 clients per VM or something. So that means that, and it's also a cloud that is being used by many scientists in Sweden. So depending on which host in the underlying OpenStack system you end up on, the performance will vary a lot. So you can see that you have this kind of heterogeneous system heterogeneity in the client updates. Yes, so this was the cross-device simulations. Ongoing work there is that, as I said, we can see this as a case where you have relatively high-speed connects with the combiner. So we're currently doing more elaborate network connectivity modulation so that we can stress test the robustness of the network. And we're also building like a live test bed using yet some nano devices. So we will have like a realistic test of robustness in the sense where we have very poor connectivity in some cases. So we then do this over Wi-Fi. The other experiment we did was looking at the cross-silo setting where we were interested to see, okay, what happens, how does the model cope with increasingly large models and horizontal scaling. So what we did there is that so Adi here, a postdoc in the lab, did a experiment with sentiment analysis with this IMDb data set. So we did a CNN model. In either of these examples, we have tried very hard to sort of build the best model. We build something reasonable, typically taking something that we found from Kaggle and modified it. But what we did here is that we made it so that we could vary the model size from this update size from 10 megabytes to 1 gigabyte by tuning some embedding layer. And what we did then is that we sort of experiments in 4 simultaneous geographic regions of Amazon EC2. So this is really like this was a live test in the live EC2 environment. We used high-end VMs for combiners, so it was the best compute flavor, non-GPU equipped compute flavor that we had, C5s, with 16 CPUs and 32 gigabytes of RAM. And then the first sanity check that the model, that the framework computes the right thing. We always have to do that. And then we looked at, first of all, the scaling with model size. So we took, in that case, if you see this bar plot here, the first bars to the left are a single combiner, and then we vary from 10 megabytes up to 200 megabytes. And then we look at the total runtime on the combiner level. So we isolate the data on the combiner. And as you can see then, and this is completely as expected, it increases roughly linearly, a little bit worse towards the end there, on the as the model size grows. And this is what we would expect because the communication and aggregation costs should increase roughly linearly. It's a linear increase in the amount of data we need to transfer. Here I think we took 10 clients, no, 40 clients, I think it was, in total, connecting to a single ice in the paper, single combiner. But then you can also show again the idea with the good thing about having the hierarchical implementation is then for the case we then add to 2 combiners or 4 combiners, and we can actually see that the combiner round times goes down again. So we can actually scale it by adding more combiners. So here we went up to 200 MB sizes, and then we did the real stress test where we took the largest model size, so 1 gigabyte updates, the clients are streaming. The update times, I think, varied in the hundreds of seconds on each client. And then we put 4 combiners, 1 in each of these regions you see in the picture in the EC2 cloud. And each of those we then loaded with 6 clients each for a total of, well, yeah, the last one we stepped a little bit more. It was for practical reasons. So for the up to 40 clients in total of 4 combiners. And here you can also see the sort of the framework. But here we also include, you can look at all 3 of the tiers in the system. So the blue one, that's fairly constant, and that's as it should be. That's the time with the clients update. So this is just a check baseline to see that this is not changing very much. This is constant over the experiments. The combiner runtime then depends, of course, on the load in the combiner. And that is also almost constant since we keep the amount of clients per combiner constant in the experiment. This is the horizontal scalability test. Here you can see the effect of the reducer layer. So that cost actually grows because that is still a single all reduce operation. So it costs more to aggregate from 4 combiners to instead of 1 combiner. But you can also see in the bar to the right there that if we wanted to scale this network further, we still haven't saturated combiners. So we could keep adding clients a little bit a while. But here in the end, we also measured on the total throughput in the network when we were in the case with 40 clients, like the maximum loaded case. And we could see that the data flow in around was on average 150 megabytes per second, which was quite good. Yeah, so in all, these experiments were designed then to explore this hierarchical implementation and also, of course, the efficiency of FedN in itself. I think it worked quite well. We also looked at framework performance, and here we were interested in, okay, what is the overhead of the implementation? So we broke it down on sort of the parts that are directly related to the federated learning and the parts that are essentially bookkeeping, overhead in the code. And as you can see here, in this pie chart, we looked at sort of the work done by the reducer. And waiting for combiner updates, that's essentially just the work, the time it just sits polling if the combiners have actually completed a partial update or not. And then it's like essentially download and upload of models as the green and orange part. Model aggregation is a very small part, like that computation is cheap compared to network transfer. Commit model, that's essentially storing the model in an object store for forever. And then other there, that's everything that is not this. So this would be, you know, writing to databases and assigning clients, all of this business logic. And that is small, and that is as it should be if the implementation is good. Yes. So what we're doing here on the cross-silo setting now is like we're first of all exploring different applications now that we feel that we have a system that can handle quite large models. So we have a postdoc that works a bit on federated question answering systems. It's a fun application, also in connection to active learning. And then we're also looking at supporting or developing schemes where you would only transfer and update certain number of layers in the network in each of the rounds to reduce communication overhead, trade it off for more rounds. So I see, Samuel, we're nearing the end here, so I should try to wrap up. But I also wanted to mention, I mean, there's of course a lot of related work in the community, but I just wanted to highlight these two papers. So there's one that I like about analysis of the hierarchical model, the convergence analysis. And then the work we have done, I think, on the software side, the one that is most similar is this paper by the Google team towards federated learning at scale. It also employs multiple different aggregators in the implementation, but they looked more on the MTC implementation and for smaller models. But to my knowledge, that code has not been published, so that will be something if someone knows about that. But those are the two, I think, that are sort of most directly comparable to what we did. And then I thought I'd talk a little bit about some case studies, but I think I will skip that.
Sorry, Andreas, we
yes.
have one question by
Constantine.
Thank you. I think it's relative to related work slide.
Yeah.
So we do a lot of ongoing research. I would like to ask, did you spend time making comparisons with similar works like FedAvg or Flower?
No.
It's just they are like for first order, they are the same. I think your combiners ideas are very scalable, and it's slightly another work, but I appreciate any of your comments.
Yeah, so of course we have looked, and in the paper we do a little bit of comparison, but we have not done our own systematic comparison and benchmarking with all of the other frameworks. We are aware of them, of course. I think Flower is interesting. So if you look at the implementation level, I think there are a lot of similar choices in the choices of technologies employed between FedN and Flower. As far as I understand, Flower still has a single server model, so that's the difference. But I really like sort of that code base as well. It's similar, but I know that there are. I mean, our frameworks are fairly recent as well, so I know of at least one ongoing benchmark study that will look at this both from the perspective of supported features and performance. I am not, or our teams is not explicitly involved in that, but I hopefully it will come.
Thank you. One more question. I think so regarding this work, the second bullet, which is not published, but So it's more probably like philosophical question, but I'm interested in your opinion. So, some people do not publish the code. So for example, the Ruby solver, it's not publishable code. And you publish your work in open source, but in the first slide you have mentioned that you have like industrial clients, and how these things can be like coexist, like, or they can.
This is something we talk about often in the company. No, but I think it's really important. It has been really important. First of all, it's a bit of a, as you say, philosophical question. I really like open source, and I have always done that in my entire research career. So we have done several different open source projects. I think it has been also very beneficial from the perspective of having a startup that you have open source code, because it also gives you credibility in early discussions, and also reduces risk, of course, for collaborators. And there's always the code, the possibility to contribute to the code. And I think that is important for many, especially in a new field like this, where you want also to take part in the fun, right? You don't want to sit back and just get the final model. So yeah, I think that, I mean, there are very many ways to make businesses out of open source projects, and this is the strategy that Scalable has chosen to go for with FedN. Now I see we're running out of time, but I also wanted to show you, because what we are doing currently is we're making a software as a service as well. But I don't think I have time to demo it, but there's a video I can share if someone is interested, or it's on our webpage. Where we are making it drastically easier to set up these networks. So this SaaS is, let me just go here. You see this other window now. You should see a window called Scalable Studio. Is that what you're seeing? So,
yes.
Yeah. So this is something. Yeah, exactly, that we're building, where you can go and, sorry?
Yeah, I just wanted to say, please, after the talk, just send me those links. I'll include them and post them along with your talk.
Now, this one I will not send because it's not official yet. It's still in beta testing. Right. But what you can do here is that you can go and you can really put up these things in production. And this is a SaaS that runs in a Kubernetes environment. And it's designed in this case to make it drastically quicker to make application development, to make use cases with federated learning. So it handles all of these, production grade deployment issues with running a database and creating volumes and replicating pods and restarting combiners if combiners die, and all of these things that you would like to do. Also provides in this basic MLOps environments with Jupyter Lab, and you can serve the federated model that you have in the end with TensorFlow or PyTorch, depending on what to do there. So you just really quickly can get started. Now it hasn't even deployed yet, so I was too quick. But you can, quickly get started configuring these networks. So for example, if I wanted to go ahead and deploy a MNIST example in FedN, I will just go and I will look for it. Where is it? Examples. MNIST, we take the Keras version. You can just upload the package. Upload a seed model. This. And then I'm good to go. So I have sort of set up the complicated part with deploying this distributed framework. And you can, of course, also go and do it from the repository in Docker Compose or natively your own environment. But then you get this kind of UI that we have for, first of all, running things and interacting with what we call the model trail. This is the trail of global models. And eventually, if you start training this, will also show the performance, the plots that I showed you in the talk there, that it will measure and display load on the combiners and clients and so forth. So this is something that we're doing to make in the company to make it quicker and easier for clients to actually work with federated learning. Yeah, so I think I will stop there. See if there's any time for questions.
Thank you, Andreas, for your excellent talk. So we have still like maybe time for 1 or 2 questions or comments. So if you do have some, please either raise your hand or put your question to the chat, and I'll try to unmute you.
I can also mention that if you come up with question later, or if you decide to try the framework, I mean, if you want to do some research with it, we have a public Discord channel, and it's the company that runs it, Scale Out, but it's not a Scale Out people in there. It's like an open community of people that are interested in decentralized AI. When you have community support of FedN, but we also discuss like federated learning and edge, fleet and edge AI, and even some Web3 occasionally. So this is, of course, a place where you can find me as well if you have questions after the talk. And there's an invite link on my group webpage.
Thank you for sharing. So yeah, it seems that we run out of time. So thank you again, Andreas, for your excellent talk.